Welcome back. In the last video, we talked about how we would analyze limits for a rational function or a function of the form h of x equals f of x over g of x. So essentially we've got a function in the numerator and a function in the denominator. And there was 4 different ways we could handle this problem. If the value that we're using is a non-zero for the numerator and denominator, we could just go ahead and plug it right in and do direct substitution. If it is a 0 in the numerator but not the denominator, then that means the limit is going to be 0. And that we have an x-intercept at that value. If the value that we're evaluating is a 0 of the denominator but not the numerator, then the limit does not exist. We have a vertical asymptote. And finally, if the value is a 0 of the numerator and the denominator, that means we have a hole at that point, and the limit also exists. Now for this video, we're going to do an example of each of those 4 problems. All right, problem 6a says to evaluate the limit as x approaches -3 of x squared minus 2x minus 15 all over x squared plus 9x plus 18. Now, when we first approach this problem, we might say, hey, I'm going to try direct substitution. So -3 squared minus 2 times -3 minus 15, all divided by -3 squared plus 9 times -3 plus 18. So this will be 9 minus 27 plus 18 in the denominator. That's going to be 0. And then the numerator is going to be 9 plus 6 minus 15. That is also going to equal 0. So we can't use direct substitution. It looks like this is going to be the example of number 4. Let's keep going. We're going to go ahead and factor this. So the limit as x approaches -3, then the numerator needs to be factored. And for this one, I'm going to use trial and error because I know that 15 is going to be 3 times 5. And it looks like this will be the minus and this will be the plus. Then I need to factor the denominator. And it looks like the x plus 3 will divide out, which is exactly what this says. Let's go ahead and write this as a simplified fraction. It says there's a hole at x equals a. That's the thing that we divided out. So a hole at x equals -3. And then it says to substitute x equals a into the simplified function. Okay, so now I'm going to say this equals -3 minus 5 all over -3 plus 6. So this limit will be -8/3. This is type number 4. Okay, let's look at this next one. We have the limit as x approaches -4 of 7x over x plus 4. Now, if I use direct substitution, I'm going to get 7 times -4 in the numerator, which is great, but I'm getting 0 on the denominator. I'm going to go back and look at my options. It says if x equals a is a 0 of the denominator but not the numerator, then we have a vertical asymptote at that value, and that the limit does not exist. So we'll say this does not exist because we have a vertical asymptote at x equals -4. And then we can also evaluate the limit from the left, the limit as it approaches -4 from the left. Now, the way I do that is the numerator is going to be a negative number, so 7 times a negative value, and then the denominator is going to be a very small negative number. So think about -4.0001 plus 4. So it'll be negative in the numerator, negative in the denominator. That means this is going to go to infinity. And this little piece right here that I was evaluating, that goes up here with what I said. For any k where we have a value and we have something approaching 0 in the denominator, that's going to go to infinity or negative infinity depending on the signs. I can also find that the limit as x approaches -4 from the right, I'll have 7 times, again, a negative value. 7 times a negative value, so the numerator will be negative. The x value in the denominator will be a very small number, but it will be smaller than 4. If you want to plug in a number here, you could do -3.99999 just to see what's going on, plus 4. So the denominator will be positive. So I have a number in the numerator that's negative and a very, very small number that's positive in the denominator. So this will be negative infinity. The denominator is going towards 0. So that makes my limit negative infinity. And if I look at the graph, if we look at the graph of this function, we could see that matches what we have. The limit as we approach from the left is going to positive infinity. The limit as we approach from the right is going to negative infinity. And because these don't agree, this is going to be it does not exist. All right, that was type number 3. Okay, let's look at this next one. And at first, it looks like we might have a problem, but if we plug in -2 squared minus 5 all over 2 minus, and then our x value is -2. So the numerator is going to be 4 minus 5, that's -1, all over 2 minus -2, so it'll be 4 in the denominator. This is just direct substitution, and that is type number 1 from above. All right, this one here, it looks like the 2 is not going to pose a problem for the denominator. So let's go ahead and just plug in the 2 squared minus 4, and then 2 minus 1. So this is going to be 0 over 1. And let's see what this says. It says if x equals 8 is a 0 of the numerator, but not the denominator, then the limit is 0, and there's an x-intercept at that point. Okay, so the limit as w approaches 2 of w squared minus 4 over w minus 1, this is going to be 0, and there's an x-intercept at x equals 2. And then we can verify this with graphing. So here's the graph. And if we look right here, we have an x-intercept of 2. There's also another x-intercept, but this problem specifically is only asking us what's going on at x equal 2. All right, that's how we evaluate limits algebraically. You'll see that there are several problems for you to try on your own. Once you've done those, go ahead and check your answers in the next video.